Hello, everyone. Sorry I can't meet you in person this day, Thursday, April the 14th. So as I said in the email message where I told you today's class would be virtual, this was one of the days that I always knew I'd be out of town. Unfortunately, we had class canceled on Tuesday, so I would have preferred that not to have happened, but the class or the things I want to talk about actually involve going through things. The results will be important. You need to see the details, but you probably will never go through the details or many of them unless you actually teach a class on signal processing. It's the sort of thing that you do need to have been exposed to so you understand where things come from. But the main thing that we'll be using next week is the final result of some of today's exercises. But anyway, so let's get started. I'm going to share my screen so that you can see the notes, and the notes will be posted to Blackboard, so you'll be able to get them. And I'm going to start with the set 14 of the notes, which we are mostly through, but which is about Fourier transforms. So I'll begin by sharing that. So you should be able to see the notes, and basically what we had been doing last time we met for class was we were talking about eigenfunctions and things like that. And at the end of that set of notes, what I'm going to do is to show that complex exponentials are eigenfunctions of linear time invariant systems. And so, so I set one up. I remind us that we can determine what the output is using the convolution integral. Then I make the calculation using the variable s. And you can see the calculation, and what we come up with is we come up with a function h of s, which is related to the impulse response by the particular integral in the middle of this page. And this shows that complex exponentials are eigenfunctions of LTI systems. So then what I go ahead and do in the rest of the notes is I look at some specific examples. I basically show that if you've got a composite signal consisting of different exponentials, then you can use the superposition principle, and the outputs are also determined by the superposition principle. And then what I do is I go on and work a specific example of a time-shifted signal. All the details are here. I didn't omit any steps. And we had to recall a fundamental property of the delta function to actually evaluate that integral, but I've reminded you of what that is. And so we're able to calculate our h function. And then what I did is I've gone ahead and showed how superposition works by letting the input be a sum of two cosines, and I've shown you how to get the output equation. And I also show an alternate way of getting the result and showing that it's equivalent. So basically, the take-home message is that if we have a continuous time system and we use a complex exponential input, the output is given by the expression where basically the capital the term capital H of S is the system function, and that's what we're going to use from here on in. If the term S is of the form j omega, then capital H is actually called the frequency response, and that's the way in which we will most frequently use this, because S is usually going to be j omega, or in fact, S is always going to be of the form j omega. And then what I have gone and done at the end of this set of notes is simply worked another example, this time where the input is a Fourier series. And so I've determined what the output is. Again, you have all the details in the notes. And the basic point is this particular problem could have been solved by solving the differential equation of the system, but this is a much simpler result. So that ends looking at the Fourier series methods, because what we're really interested in is in Fourier transforms. And so now what I'm going to do in set 15 of the notes is to go over much of the same ground, but this time using Fourier transforms rather than Fourier series. So let's switch to set 15 of the notes. So here we are, and basically all of this set of notes is about extending the results on convolution and Fourier series to convolution and Fourier transforms. Basically what we do is we follow a similar approach, again, starting with the synthesis equation, and we determine what the system function is going to look like. And basically, the system function hj omega, capital H of j omega, is the Fourier transform of the impulse response. What that boils down to is that the Fourier transform of the impulse response is the complex scaling factor that the LTI system applies to the eigenfunction. We can use linear superposition to express the response of LTI systems to a linear combination of complex exponentials. And what I want to focus on here is understanding things in terms of periodic signals. So what we're going to do is, in continuous time, we're going to take a Fourier series representation, and we'll consider what happens when the signal is applied to an LTI system. So here is the input, which is an eigenfunction of the system, and we have already shown what the output will look like for an input of this form. And in red, I've reminded you how we do that. So basically, here are the properties. What the LTI system does is it modifies each of the coefficients individually through multiplying by the value of the frequency response at the corresponding frequency. I'm not going to rework any examples. We've done several of those. What I'm going to do is to get similar results for Fourier transforms. So using superposition, we can write this result. And then if we compare it, our starting point on the first slide, we can say what the response of the system is. And then we also know that the response and its Fourier transform are always going to be related through an equation of this form. So what that means is that we can say that the Fourier transform of the output is equal to the product of the Fourier transform of the input with the Fourier transform of the impulse function. So basically, this is the result that we're going to be using from here on in. I'm going to do a bit more justification though, and the next thing that I'm going to do is to start from the convolution integral. So if we do that and we want its Fourier transform, we can go ahead and calculate that. Again, I show you all of the steps. And we use the various properties that we've developed. And again, starting there, we prove the same result. That's a formal treatment. It's probably easier to understand. And I can also write it in Fourier transform notation. So basically, this is the result that we're going to use, or and I've shown it in both notations. You'll never have to derive these equations, but they're extremely useful in signal and system analysis. And what is this equation saying? All it says is the Fourier transform maps a convolution of the two signals into the product of their Fourier transforms. Typically, it's easier to multiply than it is to work out the convolution. So we normally analyze problems like this by taking the appropriate Fourier transforms, multiplying them, finding the resulting Fourier transform, and then taking the inverse transform to get back to what the output is. That's the process that we'll follow. And you'll see that there's been a long process of setup to get to this equation, but it's relatively straightforward in practice. So, and then what I've done is I've reminded you of the definition of capital H, and reminded you it's called the frequency response of the system. So filtering is what we're actually going to be applying this to. And one of the things to know about filtering is that typically we are going to look at frequency selective filters, where we are going to want the frequency response to be approximately equal to 1 over a range of frequencies that we're interested in. And we'd like it to be 0 over another range. And the reason that we would like that is that that allows us to not have the signal modified much in the range of interest, but to have it completely to be 0 in the range of frequencies that we're not interested in. That's why the filter is called frequency selective. So since the impulse response completely characterizes LTI systems, its transform does as well. And the basic thing is that all signals of physical or practical interest in stable LTI systems have a frequency response, or in other words, the Fourier transform exists. So if we want to extend to unstable systems, though, we have to generalize our Fourier transform to the Laplace transform. We'll do that right at the end. But what I'm going to do for the rest of this set of notes is to look at some simple examples which again, you should work through. I first look at a delta function, and then I calculate what the output is. And then I look at a differentiator. A differentiator is something I talked about a while ago, but essentially what we mean by a differentiator is something that takes the signal and differentiates it. We would normally describe it as a filter. We've talked about differentiation properties before in one of the last two sets of notes, and what we showed was that if you differentiate in time, in signal space, you can use the operational result on the right-hand side of this equation to see what happens in frequency space. So that tells us how we can calculate the transform of the output. And so we can quickly see that the frequency response of a differentiator is just j omega. And this means we now have a simple way of solving systems. And the basic idea we're going to apply this to is filtering. And that is something that I do want to cover in the classroom. So what I want you to make sure that you do is to go over the notes thoroughly on that we've done through here, but basically just know what the key results are. And next week, I'm going to work examples on filtering. And then the following week, we'll do the expansion to unstable systems, where we'll introduce the Laplace transform, and then we'll be done. I'm going to give you another test similar to the last one that I gave you, and I will give it to you at the end of next class on Thursday. And it will basically be over Fourier series, Fourier transforms, and filtering. It'll be in the same format. I'll give you several problems. You can pick which one is your test problem. And then you'll be able to turn in the rest as homework. Then I will return that to you, and you'll know exactly what your grade currently stands at in the class. And at that point, if you are happy with your grade as it stands in the class, that will be your course grade. If you want to try to improve it, then there will be a final over a limited set of material, which I will describe to you in the last week of class. But it would be an open notes final, but it would be also in class. But we'll talk more about that when I see you face to face. So again, I regret being unable to meet with you today, but I always knew that I wouldn't be able to meet with you today. But unfortunately, the weather intervened and caused us a problem on Tuesday. So all the notes will be available, and we'll look at what we have been working towards all semester, which is seeing how filters work, and that's what we'll do next week. Okay, I'll end here and get this posted for you.